All right, this is a quick review, and I'm going to try and keep it real quick before our STAR test. So, on your STAR test, do the best you can. Remember what you can. Before you begin, do a brain dump. Do whatever it is you got to do to take all that knowledge and information in your head and throw it up out of your head onto somewhere where you can see it. All right, let's get started. Physical properties of matter. There are 7 ways that you can test matter. Okay, we'll use this pen. You can measure its mass, put it on a double pan balance or a triple beam balance, and it'll tell me how much mass this is. Not how much it weighs, because that's a scale, but how much mass is in here. That means how much space it takes up. Okay. Next, it's magnetism. I can put a magnet to it and see if it's magnet or not. This is obviously not. It's plastic. Next, it's physical. Is it a solid, liquid, or gas? This looks like a solid to me. Relative density. Will it sink or float? I can get a cup of water, drop it in the water, see if it sinks or float. Next, it's solubility in water. Will this pen dissolve in the water? Not the ink that's inside of it, but this. Will this part dissolve in water? Next, it's thermal conductivity. When I add heat to this, is it going to hold that heat in, or is it going to get hotter? Okay, and next, electrical conductivity, whether matter conducts or insulates electricity. If I put this up to our circuit, is it going to allow the circuit to flow through it? And no, it's not. Next, relative density. That just means if something sinks or floats. If it's less dense, it's actually going to float. If it's more dense, it's going to sink. So if I put this in a cup of water, I'm guessing it will probably sink. And if it does, great. If not, okay, great too. Next, measurement tools. You use a triple beam balance and double pan balance in science, 5th grade science, a graduated cylinder that measures volume, and a scale that measures weight. You probably got on one at the doctor's office last time you went. And the other thing that's not on here that I want to say is a spring scale. And that's that lovely tool that has a spring and you pull it out, and it measures in newtons, and newtons determines how much force an object takes to move it. All right, next, let's talk about some constant properties of water. These are things that never, ever, ever change. Boiling point will always be 100 degrees. If you ever want water to boil, you better make sure it's 100 degrees Celsius. Next, if you want stuff to freeze or start melting, make sure it's 0 degrees Celsius, okay? All right, changes in matter. This is kind of like a water cycle. This is your shower scene, right, that we always talk about. All right, so in your shower scene, you've got a hot shower going. All right, that steam is coming out of the hot shower, but it's a gas, and it's going to hit that mirror, and when it hits the mirror, it turns into a liquid, and that's because that mirror is kind of cold, okay? And so then when you get out, you see all kinds of water droplets on the mirror. That's condensation. Next, let's talk about evaporation. When you turn on that hot shower, that hot water got so hot that it started steaming, making, steam. All right, so then your liquid then turns into gas. This can also be seen, this process can also be seen when you've got a pot of water on the stove making some mac and cheese, and the hot water is boiling, and you put a lid on it, and now it's time to go check and see if it is boiling, and you pull the lid off, and inside that lid is all those water droplets, and then the steam hits you in the face, okay? That's what those are right there. Freezing. I'm going to fill up my ice cube trays and throw them in the freezer. Okay? I filled them with water. Now they're frozen. I take those ice cubes out of the tray, and I'm going to stick it in my glass of tea, and then they start getting smaller and smaller. That's because they're melting. So my liquid became a solid, but then now my solid's becoming a liquid. And the liquid became a solid because it cooled off, and the solid became a liquid because it got hotter. All right, next. Mixtures and solutions. Mixtures is this right here. These are all Hershey's Kisses, and they're all mixed together. Are they one massive Hershey Kiss? No, they're just a mixture. So this is a combination of 2 or more substances, and they maintain their physical properties. Did they turn from solids into something else? No, they're still solids. All right, the example here is iron fillings and sand. Next, a solution. Solution is a combination of 2 or more substances. Physical properties of substances may change. Examples are salt and water. Now, my coffee. Where's my coffee at? I've lost my coffee. But in my coffee, I put so much sugar. Sometimes y'all see me do it in class. I put so much sugar in my coffee, and then I stir it up, and then it tastes like tea. Yum, 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 because the sugar dissolved in my hot coffee. All right, let's see if I can zoom that in a little better. Or focus it or something. All right, moving on. That does not look like it helped any. Does that work? What does that button do? All right, while it's focusing, I'm going to keep reading. Force and motion. All right, behavior of light. Light acts in two ways. It has two behaviors. One is reflection, one is refraction. Reflection is mirror. Refraction is bending. Think of refraction as like not Pilates, but yoga. There's a lot of bending in yoga. All right, reflection, bouncing back of light waves off a surface. This is your mirrors, guys. Anything shiny, anything with tinted windows, okay? If you can see your face in it, then that light is reflection. If you can't see your face in it, but something looks bigger, then it's refraction. Refraction is just the bending of light waves, okay, as they go through one area, from one thing to another. Cameras, eyeglasses, telescopes, those are all things that you can zoom in on, right? Zoom in, make it bigger. Eyeglasses you put on because you can't see, so it makes things bigger, right? And then water, that's when we had that glass of water until Gabby knocked it over. And it had a straw in it, and that straw looked completely broken. Thanks, Gabby. Just kidding. Haha. All right, circuits. You got open circuit and closed circuit. This one's broke. Not going to work. This one's closed. So let's see if it's going to work. You start at the battery. I like to start on the positive because I'm always feeling positive. And I'll sing my energy, energy, energy flows. Don't know the words of the rest of the song, but I keep flowing energy, energy, energy flows. Hey, oh my God, I got a complete circuit. Yay! Now, this is called a series circuit or parallel. Series. If I were to somehow have them all intertwined together, then it would be a parallel. Parallel, remember, is two or more. All right, uses of energy. Mechanical uses is turbines and dams. This thing, your arms, riding a bike, right? Riding a skateboard. Writing with my pen. That's all mechanical. Electrical, computers and lamps. This computer would not be recording me if it didn't have electricity flowing through it. All right, light. That's our solar panels. Thermal, ovens and melting, and sound. Hearing messages. Oh, I thought it said hearing massages. Hearing messages, okay? Sound is what you're doing right now. You're listening to my sound energy, and it goes up and it goes down. All right, next, force and motion vocabulary. Friction is a force that works against motion. So this pen slides pretty easy on the desk. It's really not bending, but it looks bending. That's so cool. I can't stop watching. Okay. That's if it was on a really thick shag carpet, would I be able to do that as easy to that pen? No. Okay. So friction is just the amount of force that works against the motion. Now, gravity is just what pulls stuff to the earth. Okay. You drop something, it's because gravity was stingy and wanted it. So anyway, gravity has a lot of pull around this world. That was a sorry joke. All right, force is a push or pull. I'm pushing, I'm pulling, I'm pushing, I'm pulling. And motion is just movement. So look, I am forcing this pen to move, and on camera, because there's a lag time, it looks like it's wiggling. All right. Next, this is I want you to remember melts. If you have to, write this down on your brain dump when it's time. Melts. Mechanical and electrical, light, thermal, sound. Melts. All right, good. Designing experiment of force. All right, 1, use a spring scale to drag a block on 3 different surfaces to determine if different surfaces affected the amount of force needed to move the block. That spring scale, that's that one we have in the room that you can pull on. It measures in newtons. All right, example 2, use a spring launcher to launch 4 balls with different masses, but the same volume. Measure the height each sphere reaches to determine if mass affects the distance the ball will travel when launched. The only thing I want you to remember about this for the test is you only change one variable at a time. One variable at a time. So, for instance, in this first one, it says use a spring scale to drag a block on 3 different surfaces. Those are your variables. Okay? It's the same spring scale, the same block. It's just on 3 different surfaces because you want to determine which one it goes easier on. Okay. Example 2. Use a spring launcher to launch 4 balls with different masses. So the same spring launcher, same volume. Okay, so like the 4 balls are the same size, but they're all different masses. They all weigh different amounts, okay? And then you're going to measure the height each sphere reaches. So if you have a super, super, super heavy ball, is it going to go as high as the ping pong type ball? No, the ping pong ball is going to go wee, okay? So one variable at a time. You're always just changing one variable at a time. All right, next, Earth and space. Earth and space, right here. Alternative energy resources. Silly, Baxter, Wares, Green, Hats. Okay, that's how you remember solar, bio, wind, geo, hydro. All right, this should be here. Oh, we're going to skip this one next. Slow changes to Earth's surface. Okay, so the Earth's surface changes. The ground outside changes every day. It's just so slow that you never see it. But how does it change? Well, that's that cool thing. I can't write. That's that cool process that we called WED. Not wedding, WED. Weathering, erosion, deposition. So when weathering happens, it's just breaking down of the rock into sediment. So, you've got this big giant rock out by the beach, and it's so pretty, and like people like to go and lay on it and have their little pictures taken, and like they're trying to be like a supermodel or something. But every day, weathering happens. And when that weathering, that can be wind, that can be the water, that can be the waves that wash up on it, or even ice. So every day, that huge giant rock is chipped away just a little bit each day. Next, those pieces that flake off, that's where erosion comes in. So let's say it was the wind, right, that came and blew some of that rock off. Then that wind is carrying that rock or pieces of sediment down wherever it carries it. Remember I told you sometimes you're outside and just like the wind will blow and something will fly in your eye? Yeah, that's erosion. So you can think erosion for a piece of rock or sand flying in your eye. And next is deposition. That's where it finally lands. Okay, that's where it finally lands after it's been carried off by water, wind, whatever. And like that piece of sand tried to deposit itself in my eye, but I was like, not no, heck no. And I washed my eye out, got it out. All right, so that's WED in a nutshell. All right, let's keep going. I hate that this doesn't keep focused. But if you're following along on yours like you should be and taking good notes, then you should be fine. Fossil fuels, coal, oil, natural gas. All right, Mr. Bravo in class came up with con, like a con artist, to remember coal, oil, natural gas. Fossil fuels are not good. We keep using them, and they're not good. They cause pollution. So think of like a con artist, right? They're formed from dead organisms that underwent heat and pressure for millions of years. So these organisms were once alive. After they were alive, they decided to die. Now that they're dead, millions of years got to go by and a lot of heat and a lot of pressure, and then boom, you get a new fossil fuel. And some people have brought some in to show us this year. All right, sedimentary rock formation. Sediments are deposited in layers over time. So remember, after this whole WED things happens, whatever landed here, we're going to say it's this rubber band first. Then, and over time, here, I'm going to move this over here. This paper come laying flat on it, okay? And then another layer. Let's get this layer, this book. And then let's get this jar. And then let's get these tissues on top, which you can't really see everything right now. But anyway, I'm all this layers of stuff. And now I'm going to press down, because I'm pressure and it's really, really hot. And hey, we're going to throw a little water in the mix so that everything kind of sticks together, okay? Because, sometimes it rains and water gets in there and sticks together. And then millions of years later, you pull everything apart or you get dug up and it's all flat. Now pretend everything is all flat and meshed together, but you get what I'm saying. Do you understand that the rubber band was the oldest piece because it was the first one? Okay, that's important to know. All right, let's keep going. All right, renewable resources. Air, plants, animals, and water. I also want sun on here because the sun, these are all things that we can use over and over and over because they're always there. Air is always there. Sun's always there. Plants, animals, water. Okay, these are all renewable resources. You can use these things and turn into those things. Air for the wind, plants for the bio, animals for the bios also, water for the hydro, and sun for the solar. I'm having brain farts apparently. All right, let's talk about some cycles in space real quick. Day and night. What happens for day and night? Day and night happens because the Earth spins on its axis once every 24 hours. Guys, if you don't remember anything, please remember this. Once every 24 hours, the Earth actually spins on its axis. So I'm going to take this cup and I'm going to mark it with this. There's America. Here's the Earth. Okay, one time around will be 24 hours, like a whole nother day. So right now, let's say it's 12 o'clock p.m. It's high noon. This camera is the sun. Remember, the sun's always directly above you at noon. Okay, we're turning, we're turning, we're turning, we're turning, we're turning, we're turning. Now, can the sun get direct light to America over here? No, don't think about these clips. No, this is all in the dark, okay, because it's nighttime. And then it's turning, it's turning, it's turning, it's turning, it's turning. Oh, the sun, America's coming back around to the sun. So the sun's coming up. Yay. Thank you, sun, for coming back up. All right. How does sun rise and set? Ew, east to west. All right, lunar, caused by the moon revolving around the Earth every 29 days. Every 29 days, that moon makes a trip around Earth. Every 365 days, Earth makes a trip around the sun. Every time you have a birthday, you just went on another trip around the sun. Tides are caused by the pull of gravity by the moon every 13 hours, and seasons are caused by the tilt of the Earth's axis, and it changes every 3 months. All right, water cycle. Okay, real quick, you've got evaporation. The water comes out of the ocean. It condenses in the clouds. Then precipitation happens. It rains down onto the ground. Now, two things happen when precipitation hits. It can come and be runoff, like it just runs down back into the ocean, or all the trees and plants that got wet, and they use that water. They absorb the water to help make photosynthesis, but then now all of a sudden they don't need the extra water, so it transpires out of the leaves. It basically evaporates out of the leaves, but it's got its own fancy word called transpiration. All right, next, planets from the sun. I'm pretty sure everybody's good on this one. My very excellent mother just served us nachos. But how do you remember which one is Mars and which one's Mercury? This Mars is our next door neighbor. See, Mars is our next door neighbor. Hello. And we're doing Mars exploration every day. All right. Organisms and environments. Photosynthesis requires carbon dioxide, water, sunlight, and oxygen. I'm sorry. Photosynthesis is carbon dioxide, water, and sunlight all working together to make oxygen. Okay, so we say that the leaves and trees and everything help us. This is how they need these three things to make us oxygen. They need the carbon dioxide that we give them, and they need the water, and they need the sunlight, and then they give us our oxygen. Thank you. Decomposers they break down dead plants and animals by eating and pooping, right? Examples are mold, bacteria, earthworms, and mushrooms. Food chains, real easy. Where the arrow goes, the energy flows. So you've got your sun producer would be grass. So we're going to say that's grass. Your herbivore would be the cow. And your carnivore is going to be me because I had a big steak last night. So I can say, thank you, cow. Thank you, grass. Thank you, sun, for all the energy I have today to make this video. All right, next, food web vocabulary. Producer makes its own food. That's that grass, right? Consumer must eat to get energy. That would be you and me. Herbivores eat only plants. Those are the weird people. Okay. Omnivores eat plants and animals. So when they eat the plants and animals, those are like probably some of you in the room, like you eat your meat and your veggies. If you get a hamburger, you have lettuce, tomatoes, and the patty, the beef. Or you could just be carnivores like me and only like meat, don't like anything else. All right, a unique niche is an organism's role in an ecosystem based on how it gets its food. So a seagull How does the seagull get its food? It flies over the ocean water and then sticks its beak in and grabs food and takes it out. Okay. Next, adaptations for survival. You got mimicry, color, thorns or spines, pleasant or unpleasant odor, sharp teeth, sounds, fur, camouflage. All these are just things that an animal does to survive. They're adaptations, things that they've either been born with or learned to do to help it survive. Unpleasant odor, that's your skunk, right? All right. Traits and behaviors, inherit traits passed on through genes from parent to child. Examples are hair color, spines on a cactus, shape of a beak. Learned behaviors, learned from someone or from experience. Examples are an animal learning tricks, a child riding a bike. Okay. Insect life cycles, you've got complete metamorphosis. Remember, complete 4 equals a dollar, so it's complete. Egg, larva, pupa, adult. And these 4 stages, they are actually drastic stages. But in the incomplete metamorphosis, the 75 cents, is your egg, nymph, adult. And in the nymph and adult look almost just alike. There might be a couple small differences, but really it looks just alike. Okay. Ecosystem. That's the interaction between all living and non-living things. So, the chickens in my backyard story, go back to that. If you don't remember, I have chickens in my backyard, but they use their coop for shelter. The water they drink is not living, you know. And then carbon dioxide oxygen cycle. That's where we breathe in oxygen that the trusty little plant makes us, and we give it back the carbon dioxide. They take the carbon dioxide and they use water and sunlight to make oxygen, which comes back to us. So it just makes a cycle. Okay? All right. If you have any questions, let's talk about them today. Good luck tomorrow, guys. You got this.